Our second to last to go up here is Jerry Yang and his mentor, Pablo says Parkinson. Would you like to introduce your intern?
Of course, yeah. I hope you can hear me okay. First of all, I want to thank Ariana, Lynn, and all the N3 organizers. I mean, this program has been fabulous, and I think it's the range of topics and mentors and mentees that you've attracted is really quite impressive. And Jerry, of course, has impressed me tremendously. I mean, he's so passionate about both astrophysics and computer science, data science, and so his project, I think, reflects both his skills and his how well he's performed. And both he and I traveled a little bit over the summer, so we had to juggle time zones, but it's been great. It's been he's made so much progress every week, and I think that you'll be very impressed with what you see. So Jerry, please take it away.
All right. First, can you hear me? All right. Yes. Here we go. This presentation is a little long. Applying deep learning to gamma ray astronomy using neural networks to build a pulsar versus active galactic nuclei classifier for Fermilab data by Jerry Yang and Pablo Parkinson. So, what are gamma rays? Gamma rays are the most energetic form of electromagnetic radiation, so they're a pivotal part of high-energy astrophysics. Gamma rays originate from some of the most extreme and exotic high-energy sources in the cosmos, such as quasars, supernovae, and colliding neutron stars. Thus, observing gamma rays allows us to find, observe, and acquire information about extreme high-energy astronomical events which cannot be reproduced in labs. The information here can tell us a lot about how matter and the laws of physics behave under extreme conditions. This can give us insight to a plethora of scientific questions, such as how subatomic particles interact, or what were the first moments of the universe like. Gamma ray astronomy is one of the most difficult forms of astronomy. First of all, gamma ray astronomy must be done in space. Our atmosphere blocks most gamma rays and their traces, so we must haul our equipment into space, which is expensive and poses difficulties. Second of all, a lot of filtering needs to be done. Most gamma rays are created when cosmic rays interact with the interstellar medium or the surface of a celestial body. And also, cosmic rays mimic gamma ray behavior. So we have to filter all of this out. Another problem is that we cannot bend or focus gamma rays like regular light. Therefore, most gamma ray telescopes are more akin to particle detectors rather than optical devices. Gamma ray detectors provide relatively low resolution data, and their performances range wildly based on the energy of input photons. And this further complicates the analysis of observations. Finally, gamma rays originating from exotic events are rare. We only get handfuls of photons from a source per day, so we don't have much data to work with. Fermilab is an orbiting telescope specialized to detect gamma rays. Using its capabilities, which trump previous gamma ray telescopes, it gives the gamma ray astronomers an unprecedented opportunity to observe and study the gamma ray sky and provides answers to some of the most pressing problems in astrophysics and other high-energy fields. The duties of Fermilab are to observe sources emitting gamma rays and capture exotic events such as gamma ray bursts, use observations and captures to construct the map of the cosmos seen in gamma ray light, and determine what is emitting these gamma rays by identifying and classifying observations accordingly, such as distinguishing if an observation is an active galactic nuclei or pulsar. The sources observed by the Fermilab are compiled into catalogs that can be used by astronomers for analysis. Pablo's research works with the 3FGL catalog, and I'm working with the latest 4FGL DR4 catalog. Now it's time to introduce another important background topic. What is deep learning? And how is it different than AI and machine learning? The entire premise of AI is getting computers to mimic human intelligence and performance on certain tasks for automation and other purposes. This can be simple as programming a video game character to do certain things based on certain conditions with if loops. Machine learning is a subset of AI that takes a more ingenious approach. Instead of conventionally pre-programming algorithms of rules and patterns, machine learning uses self-adjusting algorithms that can train themselves and learn patterns from input and output data, allowing it to perform a hard task with remarkable quality. Deep learning is a further subset of machine learning that uses artificial neural networks. They're very inspired by how our brains work. These neural networks can be extremely large and capable, and their sophisticated nature allows for unprecedented accuracy and handlings on tasks of extreme complexity. One important part of any astronomy is to identify the observed sources. This part in gamma ray astronomy is extraordinarily difficult due to the low resolution, high energy readings, and sparse amounts of data we get from Fermilab. Determining what a source actually is based on the basis of a source data can be time-consuming and arduous, as a few other interns have said. The good news is that we can use AI to automate and speed up this process. Pablo's and his fellow scientists in his past research have used various machine learning techniques to build a pulsar versus active galactic nuclei classifier for the 3FGO catalog containing 4 years of data. He used variants of logistic regression and other machine learning algorithms, and his team did a great job, exceeding 94% overall accuracy with most of his methods. Our final accuracy was the average of multiple test accuracies obtained. With the powerful deep learning neural networks that I'm going to make, we hope to make a classifier with unprecedented and extraordinary capabilities. Here's the roadmap for my project. In phase 1, I'll try to implement and reproduce Pablo's experiments with the same steps and results. In phase 2, I will apply Pablo's algorithm to the latest 4FGL DR4 Fermilab catalog. And in phase 3, I'll incrementally upgrade the reproduced algorithm into a large and powerful neural network. In phase 1, I started reproducing one of Pablo's results in Python using PyTorch, a powerful and renowned Python library for machine learning. I think a lot of you who do machine learning know what PyTorch is. It's pretty cool. I chose to reproduce Pablo's simple logistic regression classifier as it yields one of the highest accuracy, and most importantly, it can be extended into a neural network. The other options such as random forest cannot be extended to neural networks, so I left them out. My logistic regression model got a final accuracy of 94.6%, which was around what Pablo got. However, my pulsar accuracy was dismal 80.2%, which was noticeably less than Pablo's pulsar accuracy of a whopping 98%. No idea how he did that. Meanwhile, my AGN accuracy was 96%, which was slightly higher than Pablo's 94.4%. The poor pulsar accuracy is likely due to the machine learning algorithms in general being very sensitive and to biases within the training data. Because our data contains around 10 times more AGNs than pulsars. However, phase 1 is overall success, and I'll move on to phase 2. In phase 2, I'll apply the same algorithm to the latest 4FGR DR4 catalog, released just a month ago. This catalog boasts many vast improvements over 3FGL, including but not limited to 14 years of data of over 7,000 sources, 344 being pulsars and over 4,000 being AGNs, accounting for more inaccuracies arising from instrument response functions. Sources are now being tested on all spectral models instead of the best fit spectral models, and the separation of some of the parameters into multiple more specific parameters. I had to take into account many of my previously used parameters being split into more specific analogs, so my model used more parameters. The results, which are averaged over multiple tests with different randomization seeds, were fairly similar or slight improvements, with an overall accuracy of 95.3%. However, there's a drastic increase in pulsar accuracy, which is now almost 90%. We think that the overall improvements is due to the latest catalog's improvements, as I used pretty much the same algorithm and data pre-processing as I did last time. Now, on to phase 3. Now I will experiment with adding possible improvements to see if the results get worse or upgraded. The phase is ongoing with more and more things being added and tested. On the screen are some improvements I've experimented with successfully. Now, some very promising results have already come out. One test yielded a pulsar accuracy of 95.8%, an AGN accuracy of 97.3%, and an overall accuracy of 96.9%. This is significantly better than the results we obtained in the previous phases. Since the results are great, I applied the model arising from this test to an entire 4FGR-DR4 catalog to generate a list of sources that are likely pulsar candidates. This could provide insightful data for future research proposals and endeavors. So in summary, this project showed the success of applying deep learning to gamma ray astronomy in order to automate the classification of Fermi-Lat sources with greater accuracy. I reproduced Pablo's previous works from scratch, applied his algorithms to the latest Fermi-Lat catalogs with successful results, and I developed a deep learning neural network that could yield phenomenal results. And even better, I was able to produce insightful data using my neural network that could greatly help assist future research proposals. In the future, we hope to use more and more deep learning and apply it to more and more astronomical data to help expedite the identification and analysis procedure. Thank you so much for listening. This project has been a blast to work on, and I feel like my favorite part of this was I was able to use this project to make to stretch my machine learning skills and to apply a lot of machine learning concepts that I wouldn't have been able to apply if I didn't have this project. This project was an ultimate opportunity for me to learn and to flex my work with my machine learning skills, and it also gave me some other good experience with stuff like research papers. So awesome. Thank you.
Perfectly on time with 10 minutes, Jerry. What a passionate presentation.
And wow, what a huge amount of work. I'm learning so much about machine learning and neural networks from all the stuff you guys are doing. We are so cutting edge with these projects.
What's funny is that I have like a bunch of
amazing.
scrap slides, and those scrap slides have even more information about machine learning.
I met with Jerry and he had about 30 slides and I was like, we know this is a 10-minute presentation. So that was a great job editing down to fit our schedule. So thank you.
Yep, and I think it's going to be the wave of the future because all of the new observatories are just making so much data. There's, even with our dedicated interns, it's really hard to get through thousands and thousands of different, images and sources. So just incredible amount of work. Good job.